Automatic, Addison.
In this tutorial, we will explore object-oriented programming basics in C++. In this tutorial, we're going to enhance our understanding of object-oriented programming in C++ by creating a class to represent a robotic distance sensor. Sensors are pivotal in robotics, providing the ability to perceive and interact with the environment. So let's open a terminal window and let's go to our folder. Opening up Visual Studio Code, open it up, type my password, if I remember it. Okay, here we go. All right, and you're going to create a file called distancesensor.cpp, and I've already got it open here. Okay, and take a nice good look at it. So first, we do #include IO stream. This allows us to use input and output operations, specifically for cout for displaying text. We declare a class named distance sensor that models a distance sensor in a robotic system. Sorry, I put my cursor so you can't see it. And what's inside this class? We have a private data member range right here, private data member called range, that's not accessible outside the class. So this encapsulation is a key principle of object-oriented programming. It protects the integrity of the data. We have a public constructor right here. This initializes the range when a new object is created. We have the initializer list right here that directly sets the range member variable. And we have a public method called display range that outputs the range to the console. This method demonstrates how objects can have behaviors through functions. Now run the code. And we get 1.5 meters. So this example shows how to define a class with the private data and public data methods. It shows how you can encapsulate the functionality in a way that's easy to manage and expand for larger robotic systems. Using classes like this helps keep your robot's code organized and modular. Okay, let's close that out. Now let's learn how to use header files in C++ to organize our code. Whether you're building a small project or a complex robotic system, understanding header files is important. Header files, typically ending in .hpp or .h, serve as a contract or interface for your code. They declare what functionality is available without specifying how that functionality is implemented. This separation between declaration and implementation is a key principle in C++ programming. Let's create a minimal example. So I'm going to start out with robot.hpp, which you can see here. Let's get rid of this right here. So this is the header file, and it contains the class declaration. Okay. And we also have robot.cpp, which contains the implementation, the actual code, and the main function. So you're going to type this code into robot.hpp. Okay, and let's walk through here. So we have #if in def, and then uppercase robot_hpp_. So robot.hpp changes to robot_hpp_, all caps. And then we do #define robot.hpp. Okay. And then at the end, we have #end if. So what is our lines 1, 2, and 9? These are called include guards. Include guards. I'll type that. Include guards. And what are include guards? Include guards help prevent the multiple inclusions of the same header file which would cause compilation errors. When you have big C++ projects, you're going to have a lot of .cpp files. You're going to be importing, like we do over here, including many header files, often the same header file and multiple .cpp files. And so you have these include guards in the header file, pound if end def and pound define, and then the pound end if, to be able to prevent errors when your code is compiling into executables. Now, the class robot is declared with a single public method, greet. Notice how we only declare what the class can do and not how it does it. And now we type the following code in a robot.cpp. Okay, and pause the video so you can type all of this code in its glory. So let me walk you through what's happening in this implementation file. We have pound include robot.hpp. This tells the compiler to insert the contents of our header file here. We have pound include iostream, which gives us access to input-output functionality. We implement the greet method right here using robot greet syntax that specifies that this belongs to the robot class. We have our main function, which creates a robot object and calls its method. And when you use pound include, the compiler looks for the specified file in the current directory first. Then it looks for it in the compiler specified include paths. An example would be usr include, like that. That directory right there. So it'll first look in the current directory. Do we have robot.hpp in this current directory? If not, let's look in one of the compiler specified include paths, one being /usr /include. Now, if you see these alligator teeth forward bracket Pac-Man type deals, so if you see these little angles right here, what this does, this is different than the quotes. This will only look in compiler specified system include paths like user include. It will not look in the current directory. So let's run this code. And you see, hello, I am a robot. So this is what you should get when you run this code. And you can see here in the main method, we called the greet method, which says, hello, I am a robot. Let's explore access specifiers in C++, which are important for object-oriented programming and robotics applications. Access specifiers determine the visibility and accessibility of class members, ensuring proper encapsulation and data protection. Now let's create a new file called accessspecifiers.cpp. And you can see I've already written it right here. I'm going to expand this out. Oh, I went too far. Okay. So feel free to pause the video at this stage and just write the code. We'll explain it in a second here. You can see the main method below. Okay, and once you have typed in all this code, take your time, by the way, no need to rush through this. So once you've typed all this code, let's just go through it and explain it piece by piece. So here we define a robot class with 3 numbers. Battery level, which is private. It's only accessible within the class. Then we have max speed, which is protected. It's accessible within the robot class and any classes derived from it. Then we have the print status method, which is public. It's accessible from anywhere, including outside the class. Now, the private specifier ensures the battery level variable cannot be accessed or modified directly from outside the class. This promotes data encapsulation and preventing unintended modifications. The protected specifier right here allows the max speed variable to be accessed by the robot class and any classes derived from it, facilitating code reuse and inheritance in robotics applications. The public specifier right here makes the print status function accessible from anywhere, allowing other parts of the program to retrieve and display the robot status. Now we run the code. Max speed 10. Let's expand all this out so I can't see anything over here. It's clear. Okay, now we can see all the output. Battery level 75, max speed of 10. That's what you should get for the output. Now let's explore the static keyword in C++. I'm going to write that down here so you can see it. Static. Static. Okay. What is the static keyword? The static keyword, I like to think of it as shared. So it really comes down to two primary uses. Number one, static variables. When a variable is declared as static inside a function, it retains its value between function calls. Number two, we have static variables, member variables, and functions. So when a member variable or function is declared as static in a class, it belongs to the class itself rather than any specified instance of the class. And I'm going to open up the static example.cpp right here, and feel free to pause the video to copy all of this code. Now, what do we do in this code? In this code, we define a function called increment counter that increments a static variable count each time it's called. The count variable is initialized to 0 only once, and its value persists between function calls. In the main function, we call increment counter 5 times using a for loop. What should we expect? So count we initialize once. It holds its value between function calls. So here we have the for loop. We should get 1, 2, 3, 4, and 5 when we run this. Let's run it and see if that's what we get. And in fact, that's what we get. You should see the value of count increasing with each function call. This demonstrates that the static variable retains its value between calls. So this example illustrates how static variables can be useful in robotics projects. For example, you might use a static variable to keep track of the total distance traveled by a robot, or to count the number of objects a robot has picked up. Static member variables and functions are also valuable in robotics as they allow you to define properties and behaviors that are shared by all instances of a class. Or, for example, let's say robot's maximum speed, or a function that calculates the inverse kinematics of a robotic arm. Let's learn about constructors in C++ and how they can be used in robotics projects. Constructors are special member functions in C++ that are automatically called when an object of a class is created. They're used to initialize the object's data members and perform any necessary setup. So I already have constructor example.cpp. And again, let's expand this out, pause the video, copy the code. So here we have this on the left, and I need to scroll on the right so you can see everything. So in this code, we define a robot class with a constructor that takes 3 parameters: name, okay, X, and Y. The constructor initializes the name, and by convention, we have the underscore after that to indicate private variable. Okay, and then the X variable, and then the Y variable. These are all the data members of the class. And then we print here, we have a stood C out right here where we print the name of the robot and the initial position, X and Y, initial position in a 2D plane. And in the main function, we create two robot objects, robot 1 and robot 2, with different names and initial positions. Now we run the code. And let's see what we get in the output. I need to push this up again. You should see messages in the terminal just like this, indicating the creation of two robots with their respective names and initial positions. So this example demonstrates how constructors can be used to initialize objects in a robotics project. You can use constructors to set up a robot's initial state, such as its position, orientation, or any other relevant parameters. Let's explore our next concept, which is function overloading in C++. And let's explore how we can apply it to our C++ projects. What is function overloading? Function overloading is a feature that allows you to define multiple functions with the same name but different parameter lists. The compiler distinguishes between the overloaded functions based on the number, types, and order of the arguments passed when the function is called. Here you can see overloading example.cpp. Let's expand that out. You can see it in all of its glory. So in this code, we define two functions named move robot. The first function takes a single integer parameter distance, while the second one takes two integer parameters, int x and int y. The first move robot function simulates moving the robot forward by a specified distance. The second move robot function simulates moving the robot to a specific position on a 2D plane. And in the main function, we call both overloaded move robot functions with different arguments. Let's run the code. And here we have moving robot forward by 10 units and moving robot to position 5, 7. Right there. So you can see how the system's able to determine which method to run based on the argument. So if we just have one argument, it says, oh, we need to run this one. If we got two, oh, we've got one that takes two arguments, run this one. So function overloading is particularly useful when you want to provide multiple ways to perform a similar action, such as moving a robot, but with different parameters or units of measurement. Let's learn about destructors in C++ and how you can use them in your robotics projects. Destructors are special member functions in C++ that are automatically called when an object of a class is destroyed. They're used to clean up any resources allocated by the object during its lifetime, such as memory, file handles, or network connections. And let's create a file together. Let's go through this together. Call it destructor example.cpp. Okay, and let's do actually let's start as we always do, pound include iostream class robot controller public robot. Oh, we need to do a colon here. Robot controller. Okay, let's do here our destructor using the tilde robot. Oops. Tilde. We do robot controller. And let's type a message in here. Stood, cout, robot controller shutting down. Stood in line. So this is doing cleanup, cleaning up resources. Now let's do void control robot. Let's do stood, see out, controlling robot. Stood end L. And our main function. Robot controller, controller dot control robot. And we do return 0. And it's barking at us. Control. Oh, function call. Need those parentheses. Okay, and so let's go through the code. So in this code, we define a robot controller class with a constructor and a destructor. The constructor is called when a robot controller object is created. The destructor is prefixed with a tilde and has the same name as the class. It is called when the robot controller object goes out of scope or is explicitly deleted. So in this example, the destructor prints a message indicating right here, the controller is shutting down. In a real-world scenario, the destructor would also clean up any resources allocated by the controller. The control robot function right here simulates the controller performing some robot control tasks. In the main function, we create a robot controller object named controller and call its control robot function. Let's run the code. You can see here, controlling robot, robot controller shutting down. So you should see these messages in the terminal that indicate the initialization of the robot controller. Okay. And we know it's initialized because we have the controlling robot function is called from the object. And then finally, we shut down the controller when the object is destroyed. So this example demonstrates how destructors can be used in robotics projects to ensure proper cleanup and resource management. Destructors are particularly important when working with limited resources or when managing external connections, such as communication with hardware or other systems. Thank you, and I'll see you in the next tutorial. Keep building.